Good evening, everyone. This is your session number 8 related to structure analysis course, wherein we used to solve the problems what you have covered during the current week. So this session got delayed due to some important reasons. So today we are conducting this class, which is a compensating class for the previous Saturday week class that you have expected to occur, wherein we will solve the problems related to what you have covered in the week number 8. So I think we should share. I think I should share the screen first. And regarding the assignment solutions. So for the week number 8, the solutions are already released, but still your problem solving session is pending. So we will be conducting this class today, and your regular class for the week number 9 will be conducted tomorrow. So let me introduce myself. My name is Pranam Mahajan. I am a PMRF scholar in Department of Civil Engineering from IIT Madras. So we are given this opportunity to help you in solving the problems and understanding the concepts related to the problems and that the means related to the concepts what you have covered in the current week. So this enables you to solve the assignments as well as interrelate the topics which you have covered and skillfully see how it can be done in the problems that you will be solving for that. Uh, so I hope the screen will be visible to everyone. Just wait for a second. Yeah, let's start this session. So this is your week number 8. Let me just wait for a second. Yeah, so talking about the week which you have about to complete. So this is your week number 8, in which you will be solving the problems related to trusses. So giving you a brief description about what you have covered in the previous week. So we started with the analysis of structures. We define the degree of static indeterminacy, wherein we have determined first solve the problems related to determinate structures. From week number 2 till week number 6, we have seen different types of structures like trusses, frames, beams, in which we have seen how the problems can be solved for different type of structures when the structure is determinate. So for trusses, we have utilized method of joints and method of sections. Then we have used for beams and frames moment area method, conjugate beam method, unit load method, virtual work method, depending upon the problem you are expected to solve and depending upon the complexity related to that structure. Then we have moved to moving load, wherein we have seen how the problems are expected to solve related to when a moving load is ordered to pass through a continuous beam, in which we have seen how the reactions at different supports are being calculated, as well as maximum moment and maximum shear when it will alter depending upon the proportionate of the load that is moving over the structure. So we have seen how the Mueller-Breslau principle can be utilized in determining the maximum shear force and the maximum bending moment over the structure. Then in the previous week, or I can say week number 7, we have seen some problems related to force method, wherein we have seen the steps that are utilized to solve the problem in determining the forces as well as forces in the indeterminate structure. So first of all, you need to know how the structure is, in what degree it is determinate, whether it is determinate of 1 degree or 2 degree, and then based upon the problem that is expected to solve, you will utilize the method, whether it is a force method or displacement method. We have seen the difference between the two in the week number 7, that which method will give you what kind of results. So we have seen and we have marked the difference between the both the methods in the week number 7. So talking about current week, so this week we will be solving the problem related to statically indeterminate structures, mostly trusses, in which trusses we will solve using method of consistent deformation. This is similar to what we have covered in week number 3, wherein we have utilized the principle of virtual work in determining the deformations, or you can say vertical and horizontal deflection in trusses using method of virtual work. So the same on almost same principle is utilized in determining the reaction forces in this kind of structures. So let me tell you a brief details about method of consistent deformation. So method of consistent deformation is also known as force method. So what you will do, you will apply a unit force and then you will see how the structure is behaving, and then we will apply the compatibility equation, and then we will determine the unknown force. So in this, based upon equilibrium conditions as well as the compatibility equation, we will determine the unknown reaction, and it determines unknowns in indeterminate structure that we have already told, that whatever the degree of static indeterminacy, based upon that we will determine the unknown forces in that. And finally, this method formulates a set of compatibility equations depending upon the number of redundants in the structures. Now, if I talk about the brief algorithm or brief steps that are involved in solving the problems related to force method, or for the current session, I can say for the method of consistent deformation. So your step 1 includes calculation of degree of static indeterminacy. So first you will calculate degree of static indeterminacy. So this is a brief overview about how the force method is utilized. So what you will do, you will first determine the degree of static indeterminacy. So for trusses, we utilize m plus r minus 2j. So this will give you the order of static indeterminacy in the structure. Then your second steps include selection of redundant force and moments in the structure. So second step takes into account selection of redundant forces or moments that are there in the structure. Okay, so your next step will tell you that you have to remove the indeterminacy and then find the solution of determinate structure. Okay, like what you used to do in uh, in week number 3, wherein you have to calculate the deformations. So first you will calculate all the forces in the member when due to external load, and when you apply the unit load, then you will see. So this is the third step, wherein first you will calculate the solution of the determinate structure. Fine. So next what we will do, we will remove the redundancies from the member, from the structure, and then solve the redundant structure. So structure with redundant force is then analyzed. Okay, and then finally what you will do, we will calculate deflection. So calculation of deflection for determinate structure in step number 3 that I have already mentioned. For determinate structure, and structure with redundant force. Okay, so for both these structure, we will determine the deflections. And at last, what you will do, you will utilize compatibility equation and then determine the unknowns. So this is the basic principle of force method that you will use in solving the problems related to indeterminate structure, wherein depending upon the order of the static indeterminacy, you will remove the redundant forces oblique movements from the structure, and then first solve the problem with the determinate structure, and then you will apply the redundant force and then see how much force is generated due to only that redundant force while removing all the external forces from that structure. And then finally you will utilize the compatibility equation and then determine the unknowns that are there in that particular structure. Okay, so let's solve some problems related to that. That gives you clear understanding regarding this, and it will help you in understanding the concept further. So your first question is like a brush up for you regarding for an indeterminate beam, that how you will calculate the reaction forces. So what you will do in this case, as we have already seen in the previous week, that for the different beams, how you will determine the deflections at different points. Okay, So for this structure, so this is your prop cantilever. So using the superposition principle, first I will split this whole structure into two parts. So what I will do, I will make this as a cantilever beam subjected to a uniform distributed load over the length. Fine. Plus, what I will do, I will take another cantilever beam which is subjected to concentrated force, which is the reaction due to the prop support. I will mark it as RB at the free end of the beam. So now if I mark the loading, so your loading is 4 kilonewton per meter whole along the length of 2 meter. Okay, so now you can see your structure A and structure B are now determinate. Okay, so now what I will do, I know that due to the hinge support or roller support at point B, your deflection at the support B will be 0. That I already know, that because at the support B you have the vertical reaction which is making the structure to have 0 vertical displacement at that particular point. So that concept I have utilized, and that becomes my compatibility equations. Okay, so what I will do, I will first calculate the deflection due to structure A. Okay, so as I already know, so due to structure A, my deflection at free end B, let me write it as end B, and this is your end A. Okay, so due to structure A, deflection at free end B will be equal to, please see the previous results that we have already discussed. It would be WL to the power 4 divided by 8 EI. So in week number 6, we have, no, week number 7, we have discussed a table in which there are problems or standard results, how you will get the deformations at different standard results. And if you want to verify, you can use conjugate beam method and moment area method to get these standard results. So now, due to structure B, your deflection at end B will be equal to, RB is the concentrated force at the free end. So RB L cube divided by 3 EI. Fine. So now utilizing compatibility equation, which says that deflection at roller support B in case of propped cantilever beam is 0. Okay, so therefore your compatibility equation will become WL to the power 4 divided by 8EI minus RB L cube divided by 3EI. Let me write, due to structure B, the deflection to be negative, because out of this one will be positive. I think you can write this to be positive and this to be negative. Fine. Okay. So this will become equal to 0. Now, if you solve for RB, you will get RB to be equal to 3 by 8 into WL. Okay. Now substituting the value of W and L in this. So what you will get, 3 by 8, your W is 4 and your total length is 2, and that will give you the reaction at B to be equal to 3 kilonewton. So this is how we will solve the problems using force method, wherein first we will determine the degree of static indeterminacy. So in this case, the degree of static indeterminacy is 1. Okay, and then we will remove one redundant force. So that's why we have removed the roller support. And then we have solved the problem by considering the determinate structure, and then after that we have applied the unknown force and we have seen how the deformations are occurring at that, and then utilizing the compatibility equations we got to know the value of unknowns at different points. Okay, fine. So let's move further. So your next question is, you have to determine the horizontal reaction force at support B of the following truss. Consider AE to be, or you can say axial rigidity to be constant for all the members. Okay, so if you solve for this, so first what we will do, we will determine degree of static indeterminacy. So your degree of static indeterminacy how we will calculate. So for the case of truss, we already know ds will be equal to m plus r minus 2j, and in this case your m is 3. Your reactions here are, at A reactions are 2, at B reactions are 2, horizontal and vertical, and that will be equal to 2. Number of joints are 3, and that will become 2 into 3, and what you will get, so I think your reactions are 4. I written it as a wrong. So your reactions are 4. Okay. So you will get your degree of static indeterminacy to be equal to 1. So that means your structure is indeterminate of first order. You can remove either one of the forces which are unknown and then try to solve the forces. Okay. So let's assume in this case your horizontal reaction at support B to be as a redundant force. So let me write that. So let redundant force. So I think I will write in some another way. So let the horizontal reaction at support B is the be the redundant force. Fine. Okay. So then using method of consistent deformations. So what you can say that your summation of PKL upon AE minus HB into summation of K square L upon AE to be equal to 0. Fine. So I am not going in details as you have already covered the lecture. So in the lecture, it is clearly mentioned that how this equation is arrived. Okay. So now what we will do? We will remove redundant force to get primary structure. Fine. So under this external, so let me write that will clear your doubts. So under the external loads, the member forces of primary structure is represented as P. Okay, so all the forces that will be calculated after removing of redundant force is considered as P. So let me draw the diagram. Okay, then it will be easy to understand. So now you have one truss. Okay, and it is subjected to a point load at top and you have the corresponding hinge at one end, and because of removing the horizontal force, this support will serve as roller on the other end. Okay, so now your structure is determinate. This is your length of 3 meter. This is your maximum load or the load that is occurring at the top to be 25 kilonewton, and this length is 4 meter. Okay, so now we have to find the forces in all these members. Okay, so utilize the principle of method of joints to determine the reaction forces in all the members. So your forces in the member, how it will look like. So I am writing the values. You will confirm that by applying the method of joints. So in this, how many members you have? You have AB, BC, and CA. So if you start with joint B, so you can see that in case of joint B, if we take summation of horizontal force to be equal to 0, by that you will get the force in the member AB to be equal to 0, and your force in member BC will come out as 25 kilonewton. Fine. Now, if I take another member, that is your joint C, if you take joint C, as we have already calculated, you will get the BC force to be 25. That means your reaction force will also be 25. So if we take the horizontal force will come out to be 0. That's why the force in the member AC or CA will come out to be equal to 0. So now you have calculated all the values of P. So now you have to calculate the values of K. So how you will do? So for that, now we will remove all the external loads and apply unit load along the redundant force. Okay. So since we have removed the horizontal force as the redundant force, so we will apply unit load in this direction, and the member forces due to that will be represented as K. Okay. So the member forces due to unit load is represented as K. Fine. So let me take this diagram and apply a unit load. Okay. So now in this case, you will not be having this external load. Now what you will do, you will apply a unit load in the horizontal direction. So now you are applying unit load in the horizontal direction. So now this, due to this 1 kilonewton load, what will be the member forces in the structure? So let me write again the member and the force. In this case, I am representing the force to be K. And now your members are AB, BC, and CA. Okay. So if you take the joint AB, so what you can say? Summation of horizontal force, when you make it to be equal to 0, you will get member AB to be equal to 0. When you take summation of vertical forces to be equal to 0 at joint B, you will get member BC having 0 force. Whereas when you take joint C and you apply summation of horizontal forces equal to 0, you will get AC to be having 1 kilonewton as the load. Okay. Now what you will do, we will substitute all these forces in this equation that we have already written as the compatibility equation. Okay. So in this equation, we will substitute all these values and then determine the unknown force. So your summation of PKL upon AE in this case is coming out as 0. your summation of K square L divided by AE is coming out as 1 square L is 3 divided by AE, and it is equal to 3 upon AE. Fine. Now I am substituting all these values in that equation. So what you will get? So therefore 0 plus 0 minus HB into 3 upon AC to be equal to 0, and from this you will get the horizontal force to be 0. Fine. Now you understood how to solve the problem using method of consistent deformations. Okay. So let's solve one more problem related to this. So in this, it is given to you that in the given following truss, assume the horizontal reaction force at support B is redundant. Okay, so now in the question it is already given to you that it is redundant, but if it is not given to you, you have to first determine the degree of static indeterminacy, and in this case it will come out to be as 1, and then you have to choose either the horizontal force at support A or horizontal force at support B to be the redundant force, and then solve accordingly. Okay, so first, what is given in the question? In the given following truss, assume the horizontal reaction force at support B to be redundant. Now, using the method of consistent deformations, calculate the displacement due to the external loading. That means you have to calculate this N upon AE along the horizontal reaction B of the support truss. Note, N is the member forces due to external load, removing the redundant. Small n is the member forces due to unit load along the redundant force after removing all the external loads, and AE is considered to be constant for all the members. Okay, so this is similar to what we have previously covered. So if you say in this question, if you start with degree of static indeterminacy, so your ds will come out as m plus r minus 2j. In this, how many members you have? 1, 2, 3, 4, 5, 6, 7. 7 plus 4 reaction minus number of joints 1, 2, 3, 4, 5. 5. That means 11 minus 10 equal to 1. Okay. So in this question, it is given to you, given horizontal reaction force B to be redundant. Okay. Now what you will do? You will remove the force and then draw the structure. So let me draw the structure by removing the redundant force. Okay. So this is how the structure is looked like. Fine. Now you have the hinge support at end A and roller support at end B fine. Now in this, how many how many external forces are given to you? One horizontal force is provided to you and it has a value equal to 50 kilonewton. And if I mark the supports or joints, it is like this. Okay, this dimension is 3 meter. Up to this level, it is 2 meter. And from this to this also, it is 2 meter. Fine. Now your structure is determinate as you have removed the redundant force. Now you have to determine all the forces in the member force. You have to determine member forces in the given truss due to the external force of 50 kilonewton. Okay. So how we will start? We can start by considering the moment about A to be equal to 0. So if you will do that, what you will get? You will get RB into 3, since that is in anti-clockwise direction, plus 50 into 4 to be equal to 0. And from that, you will get RB to be equal to 200 upon 3 kilonewton. Okay. So since your RB is coming out to be positive, so that means your RB is this 200 upon 3 kilonewton. And there are no vertical force. So that means your reaction at support A will be like this. Fine. Now, if I consider summation of horizontal force to be equal to 0, so that means at end A, you will also have one horizontal reaction to be equal to 50 kilonewton. Fine. Okay. Now, what you will do? First, in this truss member, we have to determine all the member forces. So we start with finding out the zero force member. Okay. In this case, you can see that force member DE and AD are collinear, and whatever member that is perpendicular to it will have force to be equal to 0. So that means your CD will be a zero force member. Okay. So that means now CD is removed. Now if we take member CE and member BC, they are also linear. So any member that is coming out of it, that means member AC, that will also be zero force member. So we are marking that also to be equal to 0. Now our truss is now simplified. We are only expected to calculate 3 forces. Okay. So now what we will do? Simple is take joint A. If you have joint A, in this, if you take summation of vertical force to be equal to 0, okay, so in this, at member AD, you will get the reaction force to be equal to, so this will be 66.67 kilonewton. Fine. So your AD will also have tensile force of 66.67. I am writing it to be tensile. Okay. So since this is tensile, okay, and if you take this member will also be having the force to be tensile. Okay, so in this member, the force will be same, that will be equal to 66.67 kilonewton. Okay, now you have calculated the force. If you take the member AB, in this, the horizontal force, if you take summation of horizontal force to be equal to 0, in this also you will get 50 kilonewton to be a tensile force. Okay. Now, what you will do, you will take joint E, and then you will take summation of horizontal forces to be equal to 0, and based upon that you will get the force in the member CE to be equal to 83.33, and this force is compressive. So if this force is compressive, that means the force in the member BC will also be compressive, and that will also be equal to 83.33. Okay. I am not complicating your values. It's like you have already covered this in week number 2, that how you can determine the member forces in the trusses using method of joint. So that is what I am applying in the simplest form. If you want in detail, you can take all these values in the and you can write them by applying the equilibrium equations at each joint, and then it will be easy for you to solve the problem. Okay, now I have determined all the reaction forces, but in my case, another case I also have to take, that is when there is a unit load applied in the section. Okay, so this will give you the reaction force N. Now I have to make the structure in such a way that what will happen when you have unit load applied at the redundant force. Okay, that is what we have seen in the principle in the force method, that how we will solve these problems. So now we will remove all the external forces. So in this case we have only one external force, that is 50 kilonewton, and what I am doing, I will apply a unit load at the point where I have removed the redundant force. So in my case, I have removed the redundant force from the support B. Okay, so in this I will apply 1 kilonewton at the support B. Fine. So let's mark all the supports. Fine. Now, if you try to calculate in this case, same you can use that this force will first be equal to 0. This force will also be equal to 0. Okay. Now, in this case, if you take summation of vertical forces to be equal to 0, that means you will get RA and RB to be equal to 0. Okay. And due to that, if you take equilibrium equations at joint A, you will get member force AD and BC to be equal to 0. Similarly, at the joint E, if you apply equilibrium equation, you will get member forces DE and CE to be equal to 0. Oh, sorry, I think I have done wrong here. Yeah. So first we have removed all the redundant forces. Now what we will do, we will take joint E. In joint E, there is no force, so your member forces at DE and CE will also be 0. If you take joint C, there is no additional force, so your BC will also be coming out to be equal to 0. If your BC is equal to 0, that means if you take joint B, you will get AB as 1 kilonewton tensile force, and your AD will be equal to 0. So these all are your small n values, and small n is already depicted in the question, that this is forces in the member of truss due to the unit load applied as a redundant force. So how we will solve this? So we will make a table in which we will write the members. Okay, so how many members we have? We have AB, BC, CE, ED, DA, and one more is also there, DC and CA. So total 7 members are there. Okay, now we will write the capital N force. So your force, which is capital N, how much value we got here? Your force, which is small n, how much value will dot, and then we will apply summation of n, and L. Okay, or I think L should also be written, or no, we will directly write n, and L. Okay, so in this case, what are the values of capital N you got in the truss? So for AB, it is 50, BC is minus 83.33. I am taking compressive forces to be equal to negative. CE like this. ED 66.67. DA is also 66.67. Your DC is 0 and your CA is 0. Now talking about small n. So in small n, all the forces are 0 except one, that is AB. So I will write here 1, 0, 0, 0, 0, 0, and 0. So that means your N and L is coming out to be 50 into 3, that is 150. Other all are 0. Okay. So if you take summation of N and L upon AE, it will come out as equal to 150 upon AE. So that is what is asked to you in the question number 3. Okay. Now we will move to question number 4. In question number 4, it is same a part of question number 3. In this, now they are expecting you to calculate the displacement due to redundant force, that is summation of N square L upon AE. Okay, so we have already calculated the values of N and L upon AE. Now your summation of N square L upon AE, but your N are mostly 0 except in one case, that is in AB. So your values will be equal to 1 square 3 upon AE, and it will be equal to 3 upon AE. So what they are trying to do, they are making the method of consistent deformation to be divided into different questions, and then they are collaborating, and then it will make a total single one question. So question number 4 is simple to you because already all the values you have calculated in question number 3. Okay, so your next question is, you have to calculate the member forces in AB and CE. So before that, we will first utilize the method of consistent deformation. So using method of consistent deformations, what we have already written, like your summation of N and L upon AE minus HB summation of n square L upon AE to be equal to 0. That means your summation of n and L upon AE you have already calculated as 150 upon AE minus summation of horizontal force into summation of n square L upon AE we have calculated as 3 upon AE, and that is coming out to be equal to 0. Now if you try to solve the value of horizontal force HB, it will come out as 150 upon 3 equal to 50 kilonewton. Okay. Now after calculating the value of horizontal force, if you are expected to calculate member force AB and AC, member force AB and CE, how you will calculate? So member force AB will be equal to FAB. First will be due to, that will be equal to, I will write it as N, capital N AB minus small n AB into HB. Okay, so that will be equal to capital NAB we have calculated as 50 minus small NAB, which is 1, and your HB you have calculated as 50, and that will be equal to 0 kilonewton. So your force in member AB is coming out as 0, whereas in member force CE, your force CE to be equal to capital N of CE minus small n of CE into HB, and that will be equal to capital N of CE is minus 83.33, small n of CE is 0 into 50, and that will be equal to minus 83.33 kilonewton, which will be a compressive force. Fine. So this is how you will solve the problems related to method of consistent deformations. So now one more problem is there. So what will happen when your degree of static indeterminacy is not equal to 1? Okay. So in that, how you will solve the problem if your degree of static indeterminacy is more than 1? Okay. So let's see this question. So this is the question. In this, it is telling you first to calculate the degree of static indeterminacy. Okay. So first, how you will calculate static indeterminacy? That will be equal to m plus r minus 2j. In this question, how many members are there? 1, 2, 3, 4, 5, and 6. Total 6 members are there. Reactions are 4 because 2 hinges are there, minus number of joints, that will be equal to 1, 2, 3, and 4. Okay. Internal, there is no joint. They are overlapping members. So here you can assume that member AC and member BD are overlapping members. They are not jointed at the intersection point. Okay. So here what you will get, 10 minus 8. So your DS is coming out as 2. Fine. So now earlier in all the problems you are getting the degree of static indeterminacy to be equal to 1. But now in this case you are getting it as 2. So what you will have to do. So in this case, the structure is indeterminate of second order. Fine. So let's see how we will solve this problem. Okay. So to solve the problem using method of consistent deformation, we need to solve the equation. So this is the equation where you will be having two unknowns d1n and d2l. Okay. Plus the flexibility matrix multiply by the unknowns, which are the redundant forces in the structure, and that will be equal to 0. So this is your consistent deformation, and it is similar to what you have covered earlier, wherein d1l here is given to be to you as the assumed displacement along the member force BD and along the horizontal direction support B respectively. Fine. And these are due to external loads after removing the redundants from the structure. Whereas F is the flexibility coefficient and capital H is the redundant force. Like you used to take this as the HB in the previous question, and this flexibility matrix to be equal to small n. So I will write it to be here as the summation of capital N and L upon AE. So this is your capital D. This is your small n square L upon AE. And this H1 and H2 your HB. So this is how you used to solve previously. Okay. Now, since you have two unknowns, so how you will solve them? And these two unknowns, they are not decoupled. That means they are not separate from one another. There is one interrelation between them, and that interrelation is given to you by this F12 and F21. Okay. So that's why we don't solve the problems or equations separately for this case. We have to use the matrix method and then determine the values. Okay. So here in the question, as it is already given to you, which are the redundant force. So here, horizontal force, horizontal reaction at B and member force BD is considered as redundant. Okay. You can choose whatever you want. If you want to take AC also, you can take AC also as a redundant force. Okay. But in this current situation, as it is already given to you in the question, so we are taking the horizontal reaction as well as the member force BD to be the redundant. Now, what we will do? We will remove these redundant forces. So, remove the redundants and determine the member forces due to external loads. Fine. So first we will draw the diagram that will clear all the doubts. Okay. So in this case, now since a reaction force is removed from this, so that means roller support will come at support B. So talking about the additional forces that are expected or that is given in the question. So you are having reaction forces in this structure. So this is your 50 kilonewton. This is your 60 kilonewton. This is 80. And if I mark the support reactions, this is your A, this is your D, this is C and B, and these are 8 meter and 6 meter respectively. Okay, so now what I need to do, I need to calculate all the capital N values in this structure after removing the redundant forces. Okay, so let me bring this diagram in the center. Okay, now we have to calculate all the reaction forces. So this is your N, capital N. I will write it here. Okay. Now, if we take joint D, so what you will get? So in joint D, if you take summation of vertical forces to be equal to 0, you will get at AD equal to 50 kilonewton as the compressive force, and your member CD to be equal to 0. Fine. Again, if I take the reaction forces, okay, in this case, so if you determine the reaction force RB, what you will get? You will get, if I take summation of, so if I take moment about A to be equal to 0, you will get RB into 8 minus 60 into 8 plus 80 into 6 to be equal to 0, and from this you will get reaction RB to be equal to 0. Fine. This is okay to you? As reaction RB will be equal to 0, that means your reaction RA will come out as 10 kilonewton. I will mark it here. Your reaction RB to be equal to 0. And if now I'm using summation of vertical forces to be equal to 0, you will get RA to be equal to 10. Fine. Since RB is equal to 0, that will give you member BC and member AB to be having the 0 force. And since these are 0, so that means your member AC, if you take joint C and apply equilibrium equation, you will get the member force AC to be equal to 100 kilonewton, and that will be a tensile force. Okay, so you have to solve this problem. You can use the method of joints at each and every point and then see what are the forces you are getting in this proper structure. Okay, now what I will do, I will remove all the external loads and apply unit force along the member BD. Okay, so let me take this as a diagram and see how can I use this. Okay, now I am solving for N1. Let me write it here. This is N1. where N1 is happening when you will remove all the external forces. Okay, so I am removing all the external forces, and I will apply unit load in the redundant force direction. So this is your redundant force direction. So this is your 1 kilonewton force. This is again your 1 kilonewton force. Okay, now if remove, so now I have to calculate the forces due to these loads in the structure. Fine. So in this case, these value will not be 0. Now we have to calculate the member forces in all of these. So how you will do? You will take one joint and then try to determine the reaction forces. Okay. So in this case, if you take summation of vertical forces to be equal to 0 in member BC, oh sorry, at joint D, so you will get the forces to be equal to 0.6 compressive in this case and 0.8 compressive in this case. Whereas if you take joint D, you will get 0.6 compressive here and 0.8 compressive here. Fine. Now let's talk about what will happen if I remove all the forces and apply redundant force on the support. Okay. So in that case, what will happen? So if let me write it to be N2. So in that case, let's remove first all the forces. These values will not be there. Okay. Now what we will do, we will apply a unit load along this direction, and this will be equal to 1 kilonewton, and due to this you will get 1 kilonewton as tensile force in member AB, whereas your rest all members will have 0 force. Okay, now you have calculated all the values N1, capital N, small n1, small n2. Okay, so I will make a table that will be easy for you to understand. So you have member. So how many members will be there? 6 members will be there. One is AB, AD, AC, BC, CD, and BD. Okay, so all 6 members now you have calculated. We will write their corresponding lengths. So their lengths are so their length Li, they are 8, sits, 10, sits, 8, and 10. Fine. Now I will write corresponding capital Ni values for them. They are 0, minus 50, wherein I am considering all the compressive forces to be equal to 0, 100, and rest all are 0. Okay, this is what we have calculated. Now if I calculate capital N values, small n, 1, and I is the corresponding length, and that is coming out to be 0.8, 0.6, 1, minus 0.6, minus 0.8, and 1. Okay, so this is what we have calculated. Now your N to L, N to I, how they are looking? Only one force is there. In AB it is coming out to be 1, and rest all are 0. Fine. Now you will be having the combination of the values. That is, okay. So in the previous case, it is told to you to solve the problems and calculate the flexibility matrix. So to calculate the flexibility matrix, how you will do? So your flexibility matrix F11, you have four values: F11, F12, F21, and F22. So your F11 will be equal to summation of N1 I square Li upon AE. Okay, and that is coming out, if you solve that, it will come out to be 34.56 upon AE. Fine. And I have calculated. What you have to do, you have to take N1 square L, and then you have to find out. Whereas your F22 will be summation of N2I square Li divided by AE. If you will do that, you will get the value as 8 upon AE. Now talking about F12 upon AE, so your F12 will be equal to summation of N1I, this is 1I, N2I Li divided by AE, and if you do that, you will get the value as minus 6.4 divided by AE. Similarly, if you do for F21, that will be equal to summation of N2I, N1I, Li upon AE, and that will be equal to F12, and it will be equal to minus 6.4 divided by AE. Fine. Okay, so your flexibility matrix, so hence flexibility matrix is, your F will be equal to 1 upon AE, I am taking out, so it will be 34.56 minus 6.4 minus 6.4, and this will be 8. Okay, so this is how you will calculate the value of flexibility matrix. Now next question is continuation of the previous question only. In this, it is expected to you to calculate the D1L and D2L. So your D1L is equal to summation of capital Ni, N1I, Li divided by AE, and your D2L is equal to summation of Ni small n2I Li divided by AE, and using the previous table, if you determine the values, they will come out as 1180 divided by AE, and another is 0. So that means your D matrix, will be 1 upon AE one one 80, and this is 0, like this. Fine. Now in the last question, it is given to you that you have to calculate the member forces in BD. So to determine the member forces, first we have to determine the unknown reactions or redundant forces. So how we will determine the redundant forces? We will utilize the compatibility equation that is given in the question number 6 to you. So we will utilize that and then determine the reaction forces H1 and H2, and after that we can calculate the member force BD. So what is the compatibility equation that is given to you? That is D1L and D2L. It will comprise of one matrix, that is D, that you have already calculated in previous question, plus the flexibility matrix F11, F12, F21, F22, multiply by the unknown forces, or you can say redundants. And what are the notations of redundants? That are H1 and H2. And in this case, our redundants are, one is the horizontal force at support B, and another is member force BD. And that will be equal to 0. Fine. You already have the values of matrix D and flexibility matrix. So substitute that. So that will be equal to 1 upon AE 1180 0 plus 1 upon AE, your flexibility matrix is 34.56 minus 6.4 minus 6.4 into 8 multiply by the unknown force H1 and H2, and all of this is equal to 0. Fine. So solving above, we get H1 to be equal to minus 40.08. Your H2 is equal to minus 32.8. 0.07. Okay. Now to determine the member force, so to determine member force, BD, your FBD will be equal to capital NBD that you have calculated from the determinate structure, then small n BD, N1, I think I should write N1 BD, which is proper. That is when you have applied first redundant, and due to that you will get the unknown as X1 plus small n2 BD, and you got the reaction force as H2 in this case. So if you substitute all the values, what you will get? So your capital NBD is 0. Your small n1 BD is 1 into minus 40.08, and your capital N2 BD is 0, and if you multiply by the unknown force, that is 32.07, so you got the value of FBD to be equal to 40.08 kilonewton. Okay, so this is your compressive force FBD, because we have taken the value to be negative as compressive. Fine. So that completes your method of consistent deformations, in which we have seen how to solve the problems when you have indeterminate type of trusses. We have solved the problems for first order determinacy, and then we have seen how the second order indeterminacy problems affects the solution, and in which coupling of the equations will also alter. That means you have to first form the flexibility matrix, which is not only the combination of the individual redundant forces, but also when there is interaction between first redundant force and second redundant force, then how it will affect the total solution, that will also come into picture. So as the order of redundancy increases, the more complexity will come into picture, and then more complex will be the behavior of the flexibility matrix. Okay, so this is how you will solve all the problems using the method of consistent deformations. So next week we will solve the problems related to beams, and we will see how in that cases it will affect the structure. Okay, as anyone has any doubt? So we know that this lecture got delayed due to some unforeseen circumstances previous week. So tomorrow you will have the regular class at 6 to 8 p.m., in which we will solve the problems regarding the topics what you have covered in the week number 9. So thank you everyone. Have a nice day. Looking forward to see you tomorrow.